Hello everyone, and welcome back. Okay, so we learned about those valence electrons. We also learned that some of those electrons, they just don't want to be there. There it is. Okay, back to writing. Because we always want to fill in the shells. We want to fill in the shells, those electronic shells. Now, I know when I say shell, you're having difficulties actually visualizing what that looks like. It's very complex, but just think about it this way, okay? Just imagine that there is a big spherical shell that is full of electrons. And all those atoms, they either want to have that shell completely filled, all electrons they can, or they want it completely empty. And there's multiple subshells, there's shells inside of them, and they're either super happy when they're filled, but they do not want them to be partially filled. They're going to do whatever they can to change that. Okay. Now, this is our periodic table. Atoms that are in the same elements, that are in the same column have similar valence electronic structure, and they act fairly similarly. Like these guys right here, they're the inert gases. They don't actually want any electrons. They don't want to lose any electrons. They're just perfectly happy. All of these want to gain 1 electron. These want to gain 2 electrons. These are happy to give up 3 electrons. These are happy to give up 2 electrons, and these are happy to give up 1 electron. So as you can kind of guess, these would go very well together. One wants to gain an electron, one wants to give up an electron. And that is coming from their electronic structure. Let's look at it real quick. We'll look at it we'll just do hydrogen because hydrogen is so simple. Okay, we start at the very first shell. It has an atomic mass number of 1. It only gets 1 electron. So we start at 0. That's n equals, sorry, not equals 0. N equals 1. L equals 0, which is the S subshell. ML is also going to be equal to 0, so there's only 1 orbital. And then MS is equal to 1/2 and -1/2. So you can see that for that very first shell, we want to have 2 electrons. Hydrogen only has 1 electron. Now, this might be where it confuses you because you're wondering, well, okay, it wants to give up that electron, so it has an empty shell, yes. But why doesn't it want to gain an electron? Because wouldn't that be the same exact thing? You have a point. However, based on how these work, based on the number of protons, based on the number of electrons they have, based on their size, there's something called electropositivity or electronegativity. These are more electronegative elements over here. They want electrons, they want to become negatively charged by gaining those electrons. These are electropositive over here. They want to give up electrons. And so since hydrogen's on the electropositive side that wants to give up electrons based on just its size and structure in magical quantum physics, it will give it up. It's going to always give up the electron. And we actually have a term for that. There is no electropositivity, there's only a term for electronegativity. And what you see right here is that as we go this direction, more or less, you see there is some kind of variation in here. We get more electronegative. Fluorine, the most electronegative element there is currently, maybe there'll be something else. Francium, the most electropositive currently, or at least it has the smallest electronegativity. So francium really wants to give up electrons. Fluorine really wants to take electrons. You can see that hydrogen is in between. So there is a possibility where hydrogen and something else may very well, in a very strange case, hydrogen might steal an electron from francium, just because francium is so has such a low electronegativity. Now, the reason we care about this, and when I keep on saying steal electrons, is because we're about to build into our first type of bond, or we're not quite there yet. Before we get to that, we have to talk about what happens when an electron is stolen from one atom to another. So in most ionization processes, we have a metal atom and a non-metal atom. The metal atom has so many electrons, usually, hydrogen is actually technically considered a metal in many cases, that it wants to give them up. It's like, I've got 100, who cares if I lose 1? The non-metal atom, like oxygen or fluorine, it wants to accept electrons. It wants to become negatively charged. Now, for this to happen, for one to steal the electron from the other, they have to have dissimilar electronegativities. If they're 2.1 and 2.2, it's not going to work. If it's 0.7 and 4.0, though, oh, you better believe that there's going to be an electron moving from one to the other. Okay, so now let's look at magnesium, which wants to give up 2 electrons, and oxygen, which wants to gain 2 electrons. As you can see, this is the electronic structure of magnesium. We start filling it in until we reach the atomic number of magnesium. So we have 2, 4, 10, 12 different electrons here. Then oxygen has 2, 4, 8 electrons. Now you can see right here, there's the valence electrons for this, there's the valence electrons for this one. This one wants to gain some electrons. It needs 2 more. This one wants to give them up. It needs 2 less. Okay? It needs 2 less. If you wonder what this whole bracket neon 3s2 is, it's simply saying that neon has this electronic structure. And so rather than write it all out, because that gets obnoxious real quick, we're just going to write it like it's neon and then add on to that. Now what's very interesting in this case is after they transfer everything over, we'll have magnesium, which will now have 2 more electrons, or sorry, 2 less electrons, which now has this nice stable structure. And oxygen, which has 2 extra electrons. That's what that 2 minus is standing for. Electrons are negative, so it is now negatively charged because it's got 2 more of them. Magnesium lost 2 electrons. Since electrons are negative, it is now more positive because it didn't lose any positive charge. What you see here is that both of them now have filled shells. Okay? The first and second shells are completely filled. They also have the same electronic structure. Now, this is not always the case. This is just what happens when you have a nice, happy system. They all reach the point they want to. Now, this is called an ionic bond. It occurs between this positive and negative ion. The electron gets stolen, but it's not like, this guy's negative, he just goes off on his own now. No, because of electrostatic force, dissimilar charges attract. So a negative charge will attract a positive charge and vice versa. So they're going together. They are bonded now because of that dissimilarity in charge. This ionic bonding, it requires electron transfer. One takes the electron, the other one gives the electron. Now this is usually not a 100% thing. The electron moves from one to the other, yes, but it's not all the way over there. And as they become more and more similar in electronegativity, that electron kind of gets somewhere stuck in the middle. That becomes a different bond type. Now, an example of this would be any salt they know of. Sodium chloride, which is just table salt, would be that. What you have here is a sodium ion, which is a metal, and chlorine, which is a non-metal. Both of them are unstable. And then an electron gets transferred. And what you might notice here is that if you look at this, chlorine got bigger and sodium got smaller. And that is real. That really happens. What's happening here is that because there's one less electron, all the protons that are in the center can pull those electrons in more easily. There's less holding them back. They don't have to pull as many things, they can pull harder. For chlorine, though, it gained an electron, and while that electron has a negligible size, it's moving very fast, so the cloud we see for the atom, all that positive charge that's at the center of it, its nucleus, has a harder time pulling, and it can't pull quite as hard, which means that it begins to get bigger because there's too much for it to hold back. Then our ionic bond is caused by that Coulombic attraction. Okay, now if you look at it this way, you're thinking, okay, well, if they're going to bond, aren't they going to just like overlap, like the positive and the negative charge right here? 2 atoms kind of like on top of each other? That doesn't happen. Because there is a repulsive force or a repulsive energy. This makes a lot more sense when we look at force, but we'll get to that later. And that repulsive force is because the nuclei of those atoms are both positively charged, and they don't like that. So, even though it's overall negative, the nucleus is still positive, and they're going to resist each other. Also, all those electrons from both atoms, they're going to resist each other. And so eventually we reach this point where we have a minimum in energy, where all that attractive energy from the overall negative and overall positive charge attracting each other is balanced out by this repulsive energy. If you look at this with a force graph, you'll see that it's actually where the force goes to 0. Force equals 0 when they're at a stable distance. And this is how they determine, okay, how close am I going to get these 2 ions? How close are they going to get to each other? One last thing is that ionic bonding is the predominant dominant bonding in ceramics. Sodium chloride, magnesium oxide, calcium fluoride. Calcium gives up to fluorine only once they needed 2 of them. Cesium chloride, a little bit too quickly. And that's always a metal with a non-metal. Metal, non-metal, that becomes a ceramic. Okay, everyone? So this time we learned about the ionic bond. That's the positive and the negative charge pulling each other together. We also learned that how far apart they are is determined by the energy. We want to find a minimum in the energy, or we want to find a point where that repulsive force between the nuclei, which are still both positively charged, and the electrons, which are still both negatively charged, equals the attractive force from one being overall positive, one being overall negative. Well, this helps you, and I'll see you all next time as we go into another fun bond type. Have a great day. Bye-bye.